So, we will continue with our discussion of transonic flows, flows that transition from being subsonic, which is to say m Mach number less than 1, to supersonic, which is to say Mach number greater than 1, okay, or supersonic to subsonic, either way. Either way, there is a transition from subsonic to supersonic, right? And we did this very briefly the last time, and we'll do it a little in some more detail. Inflows and outflows, accretion onto a spherical object, and as we remarked the last time, the mathematics is exactly the same. When we are talking about outflows, essentially we are talking, the physical situation we will be considering is the solar wind. And when we are talking about inflows, inflows are spherically symmetric inflows. This problem, the physical basis of this problem is accretion onto a spherical object. I should say a spherical compact object. Again, I really should not say spherical object, a compact object, spherically symmetric accretion. I really should say spherically symmetric. This is really what we are talking about, right? So, let us start off like this. We introduce mass conservation. In the following guise, we said, which is the area of a sphere, right? 4 pi r squared is the area of a sphere of radius r. So, the amount of, that's the area, and this is the mass density, right? And this would be the velocity. The velocity can have either sign, either it's accretion, which would be infall, or it's, solar wind, in which case it's an outflow. Either way, this is constant. And as we remarked the last time, this would mean, this is the area, this is the mass per centimeter cubed, and this is centimeter per second. So, what this is essentially saying is that the grams per second is equal to constant. Equivalently, I really don't need this 4 pi, this can be absorbed in the constant. Therefore, I can write this as r squared rho v equals some constant. Equivalently, if I, so remember this equation, and I choose not to, so let me write this again. And I choose not to use this form of the equation. I differentiate both sides with respect to r, okay? And recognizing that rho is a function of r, v is also a function of r, but k is not a function of r. When I differentiate both sides with respect to r, the mass conservation equation essentially becomes remember, these are straight derivatives, not partial derivatives, because of the assumption of spherical symmetry. 0 because dk dr is 0, right? So, this would be equation 1, and okay, all right. So, the next one, similarly, the momentum conservation equation, equation of momentum conservation without viscosity in viscid fluid. In other words, the Euler equation is written as I realize I was using u for the velocity in my slides, and now I'm using v. I hope you understand what I'm writing. It's not a big deal. Now, what's the new thing? We've been writing the Euler equation over and over again many times in this course. Most of the time we've been neglecting gravity. But now, of course, gravity is vitally important. Okay, so no viscosity, but gravity is included. The body forces are included. Okay, in lab situations, gravity doesn't really matter. It's good enough to ignore gravity, especially when you're, for instance, dealing with horizontal flows, or you're dealing with flows whose vertical extent is very limited. It's okay to ignore gravity, but not here. Okay, now what do? You try to combine these two equations. So the first thing is that to note is that equations 1 and 2 are invariant under okay, you can see this. It's evident from here. We replace v by minus v here, and you replace v by minus v here. It's the same equation. It doesn't matter. So, which is why, therefore, can treat outflow as well as inflow with the same two equations. In other words, we can treat the problem of a spherically symmetric outflow, which would be the solar wind, as well as a spherically symmetric inflow, which would be spherically symmetric accretion onto a compact object. Both of these can be treated uniformly using the same formalism. Now what we do is we write instead of we assume an isothermal sound speed and write P equals Cs squared rho. Now, this is equation 3. Okay, so this is another very important step. We are assuming an isothermal sound speed. So, in order to eliminate the P here, you see this P? Okay, I eliminate this P. So, I can write, so essentially this rho v, essentially what happens is this thing, this rho v equals, instead of writing minus dp dr, I can write minus, remember we had written P equals Cs squared rho, right? So, dp dr is equal to Cs squared d rho dr. You agree? So, I had a dp dr here, and instead of that I can write Cs squared d rho dr, right, minus, okay, and now I have this d rho dr, and I substitute for this d rho dr from, not here, sorry, from here. You see, I have an expression for d rho dr here. I substitute for d rho dr from the mass conservation equation into this equation here. When I do that, I get the following equation. Okay. So, equations 1 and 2 are combined to give V minus Cs squared over V dV dr is equal to, I have told you exactly what the steps are and I urge you to work them out in any case, 2 over r minus and I believe I call this equation 3, so this should be equation 4. And equation 4 is the most important equation we need to worry about. Now, what is, I mean, the main thing about this whole transonic business, you can write this, you can alternatively write this as, and this is a slightly friendlier way of writing it, I would say, alternatively, is some numerator over some denominator, where the numerator is 2 Cs squared over r minus over r squared, and the denominator is V minus. Okay. Now, what happens here? You see, we are dealing with transonic flows, remember? And in other words, flows that transition from subsonic to supersonic or supersonic to subsonic, isn't it? Okay. But the main thing is, either way the transition happens, they pass through the sonic point. Okay. So, at the sonic point, in other words, they pass through Mach number equal to 1. So, this you see, this equation becomes something like a V square minus Cs squared, and the V goes upstairs. Yeah. So, when this becomes a V square over Cs squared, the denominator becomes 0 and the numerator also becomes 0. Okay. So, in other words, at the sonic point, okay, the dV/dr assumes a 0 over 0 kind of character. Now, what do you do in such a situation? In order to deal with this kind of a problem, you don't just throw up your hands. What you do, you would remember from your 12th standard calculus, you use at the sonic point, of course. You use the L'Hopital's rule. Okay. All right. Now, let us now, so this is one thing you should remember, right? Now, let us now pay a little more attention to, okay, so we talked about the sonic point, but let us now pay a little more attention to where is the sonic point. Okay, I probably jumped the gun in writing this. Okay, we will come back to this. You might be, it's evident how the denominator becomes 0. You see, at the sonic point, V equals Cs and V squared equals Cs squared. So, it's evident how the denominator becomes 0. That's evident. Now, if you don't want, the thing to remember is that if you don't want the the dVdr to blow up, then you want the numerator also to become 0, so that you obtain this kind of a 0 over 0 kind of a situation, and then you'll use L'Hopital's rule to evaluate dVdr. So this is the thing. Now, when does the numerator become 0? Well, let's look at the numerator. Suppose I want the numerator to become 0. In other words, I force 2cs squared over r to be equal to gm over r squared, and this does not happen everywhere. This happens only at the r equals r sonic. Okay, so let us now ask, where is the sonic point? In other words, what is, okay, Rs is that place where the numerator okay, in other words, Rs is equal to over 2. You can see this. You can see this directly from here. If I want, the point is, clearly the denominator goes to 0 when v equals cs. Now, you don't want dVdr to be blowing up. If the denominator goes to 0 and the numerator remains non-zero, right, dVdr blows up, it becomes infinite. I mean, if that's not, if you want to avoid, if you want dVdr to have a well-behaved nature, remember we are talking about smooth flows here. We are talking about flows that do not exhibit abrupt jumps, okay, that are smooth and mathematically well behaved. So if you want the flow to be mathematically well behaved, you would demand that the numerator also becomes 0. And where does the numerator become 0? Well, the numerator becomes 0 at r equals rs. So if you are asking that the numerator becomes 0, 2cs squared over r has to be equal to gm over r squared, and that happens at an r which we will now call the r sonic equals gm over 2cs squared. So this is the so this rs is the sonic point. Okay, this is the answer to this. Where is the sonic point? Well, this is the sonic point. Okay, now even there, and that's where, so this is, I forgot to put this, I should have had this slide later, but that's okay. I mean, we've discussed this. So the denominator becomes 0, and in order to ensure that the dVdr remains well behaved, we also demanded that the numerator equal to 0 at the sonic point. And now the dVdr having a 0 over 0 kind of character is not a problem. Okay, we know how to deal with it. We use L'Hopital's rule to evaluate the dVdr at the sonic point. Okay, now, so the general solution to equation 4, this is equation 4, this is the main governing solution. The general solution to equation 4 is v over minus log you can verify this r sonic, okay, plus over r, okay, where this is the constant of integration. This is the a constant of integration. Okay. So now, depending upon what values the c takes, right, depending upon what kinds of values the constant of integration takes, you can have several different kinds of solutions. Okay. So essentially what I'll be now showing you is just plots of this solution. You see, this is essentially a solution for v. Okay. plots of this solution for different values of the constant of integration. And this turns out to be a very rich kind of behavior. Okay. The behavior can exhibit lots of different things, and so we discussed all this. So, the different kinds of solutions different values for the constant of integration C. Okay. So, there are several different kinds of solutions here, and what this is this is the square of the Mach number, and this is the radius. That is what is plotted here. It is written here, but this is very small, you can't see it. It is V square over Cs square, which is essentially the square of the Mach number, and this is and here is where the Mach number equal to 1. Okay. Now, there are different kinds of solutions. There are 6 different kinds of solutions. This is solution 1, this is solution 2, these are solutions 3, and these kinds of solutions are solutions 4, and these are solutions 5, and these are solutions 6. Okay. So, let us now immediately see, you see, let us look at solutions 6 and 5, solutions of the kind 5 and 6 first. Okay. Now, at a given r, let us now draw a little line here. At a given r, okay, you see this solution 5, for instance, predicts 2 different values for the Mach number. Suppose I was on this curve, this outer curve. Solution 5 predicts 2 different values of the Mach number. These are double valued. This says that the solution is double valued. Same with solution 6. I draw a little thing, okay, and it intersects solution 6 at two points. In other words, both solutions 5 and solution 6, solutions of the kind 5 and 6 predict double valued solutions, predicts 2 values for the Mach number. So, 5, and that is clearly unphysical. So, solutions of the kind 5 and 6 are unphysical. They are mathematically okay, but we don't need to worry about them anymore. Okay, they are unphysical. They might well be mathematically okay, but there's no point talking about them anymore. So we really need to concentrate our attention only on solutions of the kind 1, these kinds of solution 1, 2, 3 and 4. Only on these kinds of solutions. These are the only solutions that deserve our attention from now on. Okay, and so we can quickly see what are, solution 1, for instance, you start from Mach number less than 1, okay, and you end up at Mach number greater than 1, and you pass through the sonic point. This is the sonic point. Solution 2, on the other hand, starts supersonic, starts with Mach number greater than 1, and it ends up at Mach number less than 1, but it passes through the sonic point, right? Solutions 3 and 4, however, do not pass through the sonic point. They are not transonic solutions. Only solutions 1 and 2 are transonic solutions. They are the only bona fide transonic solutions. However, this equation, admits solutions that are not transonic. This also admits solutions of the kind 3 and 4. For that matter, it also admits solutions of the kind 5 and 6. But as we discussed, solutions of the kind 5 and 6 are unphysical, so we don't bother about them anymore. What are solutions 3 and 4? Solutions 3 are the ones, corresponds to the ones which remain subsonic throughout. You see, they are always below 1. They remain subsonic throughout. Okay, and solutions 4 remain supersonic throughout. Okay. So, for instance, solutions 3 would be some sort of what are generally called subsonic settling flows, and solutions 4 are solutions that remain supersonic throughout. Okay. However, having said all this, however, our attention here will be exclusively on solutions of the kind 1 and 2. Okay. This is where our attention will be concentrated, because these are the only transonic solutions. Okay. And when we meet next, we will explore solutions of the kind 1 and 2 in some more detail. In particular, we will explore solutions of the kind 1. So, solutions of the kind 1 would correspond to, say, to the solar wind. Solutions that start out subsonic, pass through the sonic point and go on to become supersonic. Except we are talking about outflows here. So, you start from the surface of the sun, right? You have a subsonic flow, right? And it passes through the sonic point smoothly, and then it becomes a supersonic flow as you go on. Okay, and this is a spherically symmetric solution. So, we will talk a little more about this kind of a supersonic solar wind, the solutions of the kind labeled by 1, when we meet next. Thank you.